hypothesis test with larger samples, example 7. A light bulb manufacturer tested n equal 50 of its light bulbs, and that sample the proportion of defective light bulbs, p hat, 0 over 50 is 0. Does this sample provide sufficient evidence that the manufacturer meets the industry standard of fewer than 10% defective? So the null value, this value p, if h naught is true, would be 10%, which is a decimal. It's, divide by 100 and make it in decimal, 0.1. And then the other null value, that's a proportion of good light bulbs. So the p is the proportion of defectives. The other null value, q, the proportion of non-defectives of good light bulbs. 1 minus p, or 1 minus 0.1, is 0.9. So at the alpha equal 0.05 level, significant. Want to test h naught, p equal 0.1, the company does not meet the standard, versus h1, p is less than 0.1, the company does meet the standard. So what what the company is hoping to do is that they have fewer than 10% defective. So that's what they're trying to prove here. So the first step, we want to check whether n times p and n times q are both at least 5. So n times p, our sample size is 50 here. 50 times 0.1 is 5, greater than or equal to 5. And that's a yes. Now some books would say no. Different books have different standards. Some books would say it has to be strictly greater than 5, but what we'll use is greater than or equal to 5. So if it's equal to 5, that's going to be a yes. And n times q, 50 times 0.9 is 45, greater than or equal to 5, and that's a yes. So we got 2 yeses, and that means we can use the z-table to compute the approximate probabilities. Because this is just barely meets the standard here, 5 greater than or equal to 5, the z-table might not be as accurate as we might like it to be, but this is the standard that we'll use nevertheless. But, if it meets the standard, we'll use the z-table. Okay, so if h naught is true, then on the average, the sample proportion should agree with the null value. So the expected value of p hat, if h naught is true, is going to be the 0.1, same as p. And the standard deviation of p hat is this formula here, square root of pq over n. So that's square root of 0.1 times 0.9 divided by 50. Our sample size is 50. And put this in a calculator. And you can pretty much do it all in one step. Second square root 0.1 times 0.9 divided by, don't push equals until the end, because everything is under the square root. 0.042426407. 0.042426407. Okay, so I'm going to store this in memory so I don't have to retype it. And then the next step is to compute the test statistic. This is, remember from earlier in the semester, the z-score, score minus the mean divided by the standard deviation. Same idea here, except the score here is going to be our sample proportion p hat, which is 0 out of 50, or just 0. And the mean or expected value of p hat is going to be 0.1. That's the same as the null value. And the standard deviation of p hat, if h naught is true, we just computed 0.042426407. Okay, so so again, we have to do the subtraction in the numerator first, because that comes before a long division bar in the order of operation. So 0 minus 0.1 is negative 0.1, and then divide by the denominator there, 0.042426407. see what we get. So it's 0 minus 0.1 equals, I have negative 0.1, and then divide by, and recall this from memory, and it's approximately negative 2.36. Okay, so the next step, because we're doing a left-tailed test, and because our z-table is left-tailed, we look up the same sign as our test statistic. So we want the probability of z being less than negative 2.36. And the left-tailed test, our tail is left-tailed, so we don't need to change the sign here. We just look up directly in row negative 2.3 and column 6 of the z-table. Okay. So row negative 2.3, and go across to column 6. You probably can't read this very well, but it's 0.0091. And that's going to be our p-value. Okay, so that's less than alpha, which is 0.05. So that means we reject H naught with 95% confidence. And conclude that the company meets the standard. It's fewer than 10% defective. Okay, so this one actually, we could use the exact probability using the tree diagram, because usually with larger samples it's not convenient to make a tree diagram because there's thousands or maybe even millions of paths. But in this case, there's only one path where all 50 light bulbs are good. So if you remember from our previous example, where all the light bulbs are good, we just had the 0.1 times the 0.1 times to the whole tree. But in this case, it would be to the 50th power. So this will give us a more accurate p-value than we got from the z-table. So if you're using the binomial probability, the p-value is going to be 0.1 to the 50th power, and no, I'm sorry, 0.9 to the 50th power. But because they were all good, so the probability they're all good, probability the light bulb is good is 0.9. So it's going to be 0.9 to the 50th power. So on the calculator, you push 0.9, and then the exponent key looks like an up arrow there, and then 50 and equals, and it's approximately 0.0052. So that's a more accurate p-value than we would get from the z-table, but for this one, I think the expectation here is that because n times p and n times q were both at least 5, that we would use the z-table, even though the binomial probability is more accurate. And that concludes this presentation.